Okay, so we're going to use this PHET physics applet, one of many good ones from the University of Colorado. You can run this online or download it and run it off your computer. You will need to put Java on your computer. So the applet is called Forces in Motion Basics, and so just Google PHET physics applets. Forces in Motion Basics, and you should be able to find this applet and run it just like I'm doing it here. So let's play around with this a little bit. So let me activate some stuff here. So I'm going to tell it to show me the values of forces and masses, and show me also a speed clock. So what I'm going to do here is I'm going to put 50 kilograms, excuse me, for the man to push, and I'm going to set the force with which the man pushes at 50 newtons. And so this is a frictionless situation here. So it's ideal. We'll assume no friction. So we will assume that friction is not present. This is an ideal case. And then Newton number 2 then tells us that the acceleration of the 50-gram mass, that's the system that we're analyzing here, is going to be the net force acting on it in the x direction, divided by the mass that we're analyzing. The net force, if we ignore friction and air resistance as well, is simply going to be 50 kilograms. That's what I'm telling the man to apply here to the right. So we're also assuming a coordinate system positive to the right. And we have a 50, I'm sorry, fix that. I meant this to be newtons. 50 newtons is the net force, and the mass is 50 kilograms. Okay, so that's going to give an acceleration of 1 meter per second per second. So we have this clock here, and now let's see what the units on the clock are. We can do a simple experiment based on this Newton number 2. And so what I'm going to have him push for 5 seconds, and we'll see where the clock ends up. And from that, we can figure out what the units on the clock are. So here goes. 1001, 1002, 1003, 1004, 1005. Okay, so to pretty good approximation, I know from the kinematic equations that if his acceleration is 1 meter per second, if the box's acceleration, the trash can's acceleration is 1 meter per second, that at t is equal to 5 seconds, v of x is going to be 5 meters per second. And so if I did a little graph of v of x versus t, I would get something that looked like this. And in 5 seconds, so this is seconds, in 5 seconds I should get 5 meters per second, and so that means that this right here is pretty close to being 5 meters per second. So we've calibrated the clock. Okay, so now let's reset, and I'll turn these back on again. And let's apply the same force, but put twice the mass on. So we had 50 kilograms on there before, and now I'm going to put a total of 100 kilograms. Okay, so now what I'm going to do is increase the mass. So m will go to 100 kilograms. And we'd like to know what a sub x is. Okay, well, from Newton number 2, A sub x is the net force, which I'm going to continue to have that be 50 newtons. But now I've doubled the mass, 100 kilograms. And so that's now 1/2 meters per second. And so if we did a v versus t for that, it would have a smaller slope. Let me do a better job here. Something like that. Okay, so at the 5-second mark, this would now only be going half as fast as it was before, 2.5 meters per second, right? 2.5, this is meters per second here. Okay, so let's just run it and see what happens here, and see. Let me now figure out how long it takes to get to 5 meters per second, which I now know to be this first dark tick here. So I'll give it a, I'll just count here and see how we do here. So before I do this, make a prediction on your own as to how long, based on this data, it's going to take the 100 kilograms to reach 5 meters per second. And see if you agree with what we get. 1001, 1002, 1003, 1004, 1005, 1006, 1007, 1008, 1009, 1010. Okay, pretty close to 10 seconds. Okay, does that make sense? Well, if it took 10 seconds, to get to 5 meters per second, then the A would be the change in velocity, which would be 5 meters per second minus 0 meters per second over the time, which is 10 seconds. And that's 5 meters per second over 10 seconds, which is 1/2 meters per second squared, in agreement with what we did here. So this is the experimental, if you will, and this is this right here. This right here, I'm going to circle it, is theory. Okay, so I'm going to let you guys play around with different combos here, and let's go on to another scenario.